Hey everybody, I was doing the intro. I was all ready, hit the wrong button. I keep hitting the wrong button. That's been totally the thing that I think I'm hitting the intro button and I'm like, there's the button. I'm just like ready to go. And I'm just like, well, there I am on screen on my monitor right there. So there we go. We're here right now. We're just reviewing for the final. Brian doesn't know how to work Streamlabs anymore. I don't know what's going on. How's everyone doing? We could start by maybe talking about the formula sheet. We could do some example problems. If you're here watching live right now, say hey in the chat. Mubot's here. I'm going and grabbing that formula sheet to see if people want to talk about it. But if you have questions, let me know. I figured I would just hop on live right now and see what questions people have. No one said anything in the chat yet. Abby, good to see you here. So Abby's here. Who else is here? Let me grab the topic sheet. Here is the topic sheet. Got it open. Oh, wait, we've done topic sheet. We've done the full topic sheet. So let's bring the formula. That's a practice test. What am I doing? Where is that formula sheet? Formula sheet. There we go. That's the one we wanted. Formula sheet. Let's see if anyone else is in the chat right now. Good to see you here, Grace. Feel free if you have a question, let me know. What topics are you covering? What do you want to know about? We'll hop over to the main screen. Formula sheet. Oh, my parrot's still here. Still got the parrot from the Kahoot. He's gone now. He flew away. Let's see. Lots to cover with the formula sheet. Just kind of understanding. Good to see you here, Megan. Lots to understand with what's going on right here. Make sure you understand the formula sheet. I really think it comes down to notation, 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 notation. Knowing your notation. We'll start over here. Where's my copy paste? If you have a question, feel free to ask. This is, I'm here to help you out, here to answer questions. So let me know, but this is the formula sheet. We can start. Can you talk about beta and power and the variables relating with, yeah, of course. You got your question. Let's do it. Okay. So when we talk about alpha and beta, what are we talking about? Here's the way to memorize the first thing. We talk about memorizing. We talk about how to learn it. So we have 1, 2, A, B. And then I sometimes say positive and negative. Okay, let's review what this means. What is Brian talking about when he says 1 right here? This is how we memorize it. This is a good way to put it in your head. And then you just have to keep talking about it. And the more you practice it, the better you understand it. What am I saying when I'm talking about 1 right here? Brian's talking about a type. What am I talking about? The 1 represents a what in this way of memorizing it? The more you get this down, the more you practice it. Type 1 error. So a type 1 error is related to our what level? A type 1 error is related to, like when we say, that's the weirdest alpha I've ever drawn. So when we say alpha equals 0.05, that is literally telling you the probability of the type 1 error. Now, type 1 errors I sometimes call a false positive because in like the Tiny Brian examples, when I say something like the null hypothesis is Tiny Brian is healthy, the alternative is Tiny Brian has scurvy. So this would be a false positive right here. So healthy and alternative being sick. So a false positive is when you reject the true null. So in a type 1 error, so the alternative would be sick right here. So in a type 1 error, I sometimes call it a false positive. It's context because you could reverse it and say someone's sick and let's look for evidence they're healthy. But if we think about the medical industry, a false positive is a lot of times what I think about when I think about a type 1. And if you remember from our practice in a type 1, the null is true and we reject it. And this is directly related to our error rate right here, our alpha. And alpha is our type 1 error rate. So if you increase your alpha level to something like 0.10, you will increase your type 1 error rate. Now that is inversely related to type 2 error rate. And when we talk about a type 2 error rate, we're talking about beta right here. Beta more traditionally is going to look like a, is that how it looks? I don't know, it looks like more like a cursed B, but it's a B, it's a beta. And so that's what we're talking about right here. We're talking about beta. And it's going to be sometimes thought of as a false negative. Good to see you here, Kyle. Mubot should be in the chat. And then we can do that right now. Next, Luke, you got it. We'll talk about this for about 5-10 minutes, and we'll hop to that next, Luke. You got it. Next great question right there. So in a type 2 error, the null is false and we fail to reject it. The null is false and we fail to reject it. I've seen people doing this during the test. They'll be like, dun, 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 dun. So just remember, what is Brian making right here? Brian is making the 2 like this, and then he's putting it on top right here to say it's false and we fail to reject it. That's what I'm showing you right here. Type 2, the null is false and we fail to reject it. Good to see you here, X. And then in a type 1, the null is true. So what you're seeing right here, I'm going to highlight this for you. These are my fingers when I'm doing this right here. So I'm highlighting in a type 1, the null is true and we reject it. So that's this portion right here. I'm going to click on it so you see which one. This is what I'm doing right here. In a type 1, the null is true and we reject it. In a type 2, the null is false and we fail to reject it. Good memorization techniques. Good to see you here, David. Everyone in the chat. We're going to do a ton of questions. Let's see how many we can get done. But this is how to understand what a type 1 and type 2 error is. We talk more context about them maybe later. But type 1 is your alpha level. Type 2 is your beta. You don't pick beta. The three things, which goes to the first part of the question, that tell you what beta is, like you would have to actually solve for this. We don't do power calculations in this class, but a lot of people will do them. So we have sample size, alpha, which we just talked about, and effect size. All of these, by increasing them, will decrease beta. Beta right here is your type 2 error rate, and then power will go up. Reason that power goes up is because power is the complement of beta. So 1 minus beta is power. So all power is not making a type 2 error, which is the ability to correctly reject the false null. That's what power is. Beta is when we fail to reject the false null. So this is when we correctly reject the false null. So you either fail to reject the false null or you actually reject the false null. So power is not making a type 2 error. And a powerful test will find results when results exist. So the things that increase power, like if you look over here, just follow kind of from this point right here over to, if you decrease beta, you will increase power. Well, the things that increase power would be taking a larger sample. So if you take a larger sample, that's like saying instead of sampling, let's say 10 students, I sample 100 students. Well, that's going to be more powerful, more ability to find results. You could reject at a higher level, but that's going to give you more type 1 errors. But by having more type 1 errors, you have less type 2 errors. They're inversely related, and that increases the power. The effect size is maybe harder to understand, but the effect size is the true difference between the null and the truth, meaning that I like to use examples like if you're sick. I used to do this thing in class where I'd be like, maybe I'm a little bit sick. Aha, aha. Hey, pandemic we're in right now, right? My examples sometimes seem odd when I think back on like previously. But I would be like, what if I came in and I coughed? Would you think I was sick? And everyone's like, nah, you probably just got a cough or something. You're like, you're not like really sick. Maybe something's in your throat or something. But what if I came in and I like fell over on the ground and I was unconscious? You'd be like, something's really wrong with Brian. And this is the difference in effect size. I could be sick with just a cough. Like with just a cough, you could be sick, but that's a very small difference from the truth and being healthy. But when you fall over on the ground, that's like a huge effect right there. I sometimes also talk about, for these examples, if you were to observe myself and my brother play basketball, we're pretty similar in our basketball abilities. He is better. But if you were to observe me and LeBron play basketball, there we go. That's LeBron. There we go. There we go. There's LeBron. There's Brian. And he'll put, well, can't move me around. So if you were to observe LeBron and Brian playing basketball, then that'd be a much larger difference. And it'd be much easier to reject that LeBron is better than Brian. You'd be like, there's a huge observable effect size here. Like, I don't know how much better LeBron is. Like, there's some truth that exists that LeBron is just way better than me, but it'd be way more observable. So the effect size is the actual difference. If you assume we're the same, it's way easier to reject that LeBron is way better than Brian than Brian versus Darren. So that's the effect size right here, the true difference between the null and the truth. Next question. Please ask more questions if you have them. Luke's got the next one here. Who will hop to the screen. I'll try to put some cuts in this. We got the test tomorrow, but let's do it. Luke says, can you explain how you know whether you put the does not equals greater than or less than alternative? Really, really great question there, Luke. Let's talk about those nulls and alternatives right here. Let's do it. Okay. If you have questions, let me know. When we do a question, we go right here and we say, Brian goes out and speaks to 100 random UT students and asks them how many hours they studied for finals. Brian wants to see if they studied 10 hours or not. Let's do a few things. What test is Brian doing? What graphic could Brian display this with? This. Oh, let's do this, and then let's go in here, like 1A or 1B. What's sidedness? So, how many tails? So that's fine. How many tails? Okay. Would you say the ratio of math question? It's even. It's very similar to previous tests. Like we we actually have the banks of questions where some are numeric banks, true false banks, multiple choice banks. So the tests are pretty similar from test 1 to 2 to 3, and we try to have the Canvas content give a good overview because the Canvas content actually take from the test question banks. So really good question right there. Thank you, Kyle. So with this right here, what kind of test is Brian doing? And so when you look at this question right here, you want to start. I didn't give a lot of the information, but think about what kind of question I'm asking. And if you can identify what type of test, you'll be able to go to your formula sheet and pick the right types of formulas. Who knows what kind of test Brian is doing right here? What kind of test? Brian goes out and talks to 100 random UT students and asks them how many hours they studied for final. That's kind of the key part right there. I'm talking about how many hours did you study for finals. So, I'll give it away if I say this. The mean hours studied was 11 with a standard deviation of 5 hours. So there we go. Great job, Amelia. You're 100% right. Great job. It's a one sample t-test. So this is a one sample t-test. The reason it's a t-test is because we're dealing with means, and it's just one group right here. We're not talking about like freshmen versus sophomores. And then the tests don't really have tails on it. Oh wait, I did say that, right? I was thinking of you are 100% correct, Megan. Wow, my brain just jumped a moment. No, the tests do have tails because you got one-sided or two-sided, but it's going to be a two-sided test. Sorry about that. My brain jumped a moment. It's going to be a two-sided, and why? So this goes back to Luke's question right here. I see Steven's got one too. But how many channel points do we need for the 3,000? 3,000. See if you got them. Check some points. Go ! Points. You can check your points. So how do we know how many tails this is? And I think this is the harder question. Great job. Hey, Jonathan, what's good? It's good to see you. Good to see you. I think everyone's like, finals are tomorrow, and everyone's like, I'm ready for finals. So right here, how do we know the sidedness? Yeah, we can do that next. And don't worry, we won't really have that on the test. Like we can do that as a follow-up to this one here, Lily. How do we know which sidedness this is? How do we know? So Brian's asking if they studied 10 hours or not. Oh, Keegan, we're going to do some practice. We're just practicing. So ask those questions if you got them. So how do we know if this is a less than, greater than, or not equal to? Less than, greater than, or not equal to? What does this wording here indicate to you when we say, did they study 10 hours or not? More practice, it'll be easier. It's going to be equals versus not equals. Great job, Megan, right there. And so what the null would be is that we have here the true mean hours of studied is equal to 10, and the alternative would be the true mean hours of studied is not equal to 10. And the reason is because we don't really give a preference on this. And the only thing that changes, put it in the chat, you know the only thing that changes between the null and the alternative, the only thing that you ever see change when you write the alternative, which this is a two-tailed alternative. These are one-tailed, they point to the left or the right, and this is a two-tailed alternative. The only thing you see change is the what. You write your null, and then you just change the what. The sign. Fletcher, great job right there. You're exactly right. Great job, David. That's the only thing we change when we change to the alternative. And we could say 10 hours, or if it's more than 10. So now, Brian wants to see if they study 10 hours, or if it's more than 10. Or we could just say Brian wants to see if there is evidence they study more than 10. So Brian wants to see if there's evidence they study more than 10 on average. I just don't want the text to move to the next thing. So we should say on average that the mean is greater than 10. So now David's 100% right. Great job, David, right there. If you notice the change to the wording, we're saying more than 10 right here, giving like, is it more than 10? You know, do students spend a greater amount of time studying than 10 hours? And then make sure to throw in there, you got it, Theodore. We're going to go right here, and all we're changing now is this sign. So the question wording, or the researcher question, hint, hint, for a lot of, I don't know, I think we might have a test question like that. But the researcher wording, it says that in the notes, the way the researcher words it is going to be the way the sign goes. So greater than shade to the right, exactly right here. We're going to shade to the right. And this one's a little bit interesting. Try to solve it right now. And we can do this because someone asked about the t and the p-value, so I kind of expanded upon this. See if you can take a moment right here and mark the notation. So I'm going to highlight the notation for you. See if you can write down the notation, and see if in the chat you can tell me any of the notation. Just to make sure we are not allowed to use a calculator. Yeah, you can use calculator. You can use calculator. You can use your own personal calculator. Same rules as every other test. So, what is any of the notation? Great job, Theodore, David, Amelia, Maddie, Fletcher. Good to see you all here. What do we have notation-wise here? Anyone just get the ball rolling. That's what we do during office hours, is we get the ball rolling on the notation. I'm going to change this to green. You got to do it twice or else it'll do that color switcheroo on you. You don't want that. So we got right here is Canvas accurate. Canvas should be accurate with the what ifs. That's how your grade's calculated. So, yep, Canvas should be accurate. Canvas should, because I'll put the grade in there. So it's a placeholder for it. Good question. Practice the notation right here. There's a really good opportunity to make sure you know the notation. Don't worry if you're a little bit off, because then you can usually look at the formula sheet and figure it out from there. If you get close, you're pretty good. So do we see any of the notation right here? I know someone's about to type in some notation. Someone asked for some advice, and great job. I think, Fletcher, you just got them. You're really close, Fletcher. Fletcher, you're super close, and I bet you you would get it perfectly right on the test. Don't worry, I think there's some questions. There's a few maybe that ask about notation stuff. But the only thing, Fletcher, and Fletcher, let's start over 100 points. Fletcher, great job. No one to put any of the notation. You got some great practice right there. Good work. So you are correct. This is the sample size, which makes it N. This is the sample standard deviation because it comes from a sample of 100 students. This is the sample mean. I think you got that one right. And then this one, you were so close. That is mu naught, because that's the hypothesized. Does that make sense? That is the hypothesized mean, and that's what goes right here is the hypothesized mean, which in truth, we're saying we hypothesize that it is mu. So you're kind of right. And so you are right, Fletcher. That is in our brain right now while we're doing this test. We believe that is mu, because that's what the null states, is that the hypothesized mean is equal to that. So this value currently right here is mu naught. If we were to write that in the generic form, it's mu equals mu naught. But right now, mu naught is 10. So when we do this equation right here, I'll zoom out just a little bit here and take a look at the equation. The equation is y bar. Really, I changed it to green. One of these days, my word will not be haunted, and I'll not hit random buttons. That day is not today. Y bar minus mu naught. See if you can solve this right here while I'm doing this. I made the numbers nice and easy. So can you solve this? I made the numbers nice and easy so I could solve it. What is the t statistic equal to? Brian, I wish our test questions were like that. And I'm I know. Why does the mathematics have to be harder than this? This is one you can do in your head. So what is the t statistic? See if you can solve the t statistic. Just practice through the mathematics. Make sure you solve it correctly and see if you can get the t statistic. Oh, and there's one more thing we didn't write down. Well, Mubot put that link in the chat. See if you can get the t statistic here. This is good practice. And then we're going to take more questions. Fletcher, great job. It is 2, because it's 2 divided by 0.5. So the t statistic is 2. Now, what we need to do is we need to go take this t and put it on the t applet. Mubot, where are you at? And we need to know one other thing. What do we always need to know for the t? Which you're going to see it here on the screen. You always need to know the what for the t. You always need to know the degrees of freedom. So try to answer the questions as I'm doing right here. They're not added in. I add them in at the final point right there. So I add them in after all grades are in, and then I do a final letter grade. And so it's really tough because I do it kind of I put it in, and then I don't increase your grade, because when I used to do that, people would email me when they were 0.2 away after I put 2 points on the grade, and they'd be I'm 0.2 away, and I'd be but I just gave you 2 points, and they'd be but I'm so close. And so it is, make sure it is make sure you go to the next grade level if you're there. But then I also keep it so that way the grade book doesn't get changed around. It's optimizing what I do has been very, very tough. It's please tell me if your grade is miscalculated though, because there's a lot of emails I get at the end of the semester I'm so close to the next grade level, Brian, and I'm sorry. I'm sorry. It makes me feel bad, but there's a cutoff for each grade level. And so right here is the p-value. So this is the way we shade right here. We shade with this right here. And there we go. But I do put the final grade in that way, or the final letter grade. So you can see the final letter grade on Canvas. You will see that. please contact me if it's wrong immediately. Be like, Brian, I do not think my grade is calculated correctly, and I'll make sure everything's reviewed. So please, 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 please immediately contact me if you think your grade is wrong. Even if you're wondering just a little bit, be like, Brian, can you double check this for me? You're well within your right to say, I think there's an error in my grade. So we have right here the p-value. And what does this mean we're going to do for this p-value right here? What does this mean we're going to do for this p-value? What does this mean we're going to do for this p-value? What are you going to do with this p-value here? This was just step 3 right here. We'll put the steps in the corner. So this is step 3 right here. That's step 3. Yep, they're on your final grade, which is awesome. So they are on your final grade. So if you make an 86, you get bumped to an 88. You make a 91, you get bumped to a 93. So it's really good right there. Mubot has helped out so much. What does this mean we're going to do right here? You're welcome, Ben. What does this mean we're going to do for this p-value right here? What is this p-value we're going to do with this right here? Who knows? For step 4, we are going to reject or fail to reject null. Good to see you here, Andrew. So step 4 is where we reject or fail to reject the null. And what is one thing we never do? What is the bad thing we never do in this class? What do we never do to the null? Could you show us how to do step 3 without using a t-applet? Yeah. Theodore, good question right there, Theodore. We definitely wouldn't have you do it without the applet. And everyone's saying, yeah, we never accept. Like, I was looking over the test today, and I promise you, there are things like that right there. If you heard that, like, accept is a bad word. We never accept the null. We only reject or fail to reject. I saw about like 5 or 6 questions related to this alone. Like, not trying to give away test questions here, but one of them is literally like, which of these things do we never do? And I'm like, I say this all the time. The fact someone's like, Brian, you're giving away test questions. I'll be like, no, look at the chat. They know the answer to that. I'm not saying it's on the test, but maybe I was looking over the test a little bit today. So we only really have 2 options here. We reject the null or we fail to reject. I always like to say not reject, because if you think about this, you either fail to go to the mall, or we'll put it down here. You either go to the mall or fail to go to the mall, which means not go to the mall. Like if I told you I failed to go to the mall today, that's such a great question, Elizabeth. It's because the null could always be wrong, especially in science. You're never saying you believe something, something is true. It's always like a tentative acceptance of it. So if you believe that students study 10 hours, well, then you'll continue to believe that. So the null, failing to reject the null basically means continue to believe. So when you fail to reject, it doesn't mean the null is true. It just means like you continue to believe the null. Does that make sense, Elizabeth? You're not saying the null is true. You're just saying like, I continue to believe it. So it's like it hasn't been disproved. Exactly. It's like we do not reject Einstein's theory of relativity. So Elizabeth, thank you so much, because this is one of my favorite things to talk about. Like this, why we don't say this. So it's like you could say it's the accepted theory in science, but it's like it's our current belief. Does that make sense? Like in science, the theory of general relativity is what currently explains the observation of gravity. But one day someone might come along and show Einstein to be wrong, so then we would reject Einstein's theory for a better one. So it's not that we're saying Einstein is right. We're just saying at this moment we don't have evidence to go on. And that's what it means to fail to reject. So that's why we use that specific wording right there. That's such a good question, because even when I was doing this, I was like, why don't we just say the null is true? No, we're just saying I don't reject the null or I reject the null. I wish we would just change to wording like I reject or I don't reject. So I think it's better. Great questions right there. Yeah, it's similar to previous exams. I couldn't remember how many I counted, but it's very similar in length. What other questions, in your opinion, is this exam harder or easy? It's very similar to exam 2, but it's like you kind of know it or you don't. Julio, do you want to call and say hey to them? And just, if you want to, you know how to call. Julio, if you want to, thank you so much, Julio. Just you being here. You don't have to do anything. You're probably with family right now. I just see Julio. You make me smile every time. That's Julio Bourbon, if you didn't know. Played for UT baseball. Just absolute, just cheerleader for our class. Just really just bringing positivity to all students. And I really appreciate that. So keep asking those questions. I don't mean to put Julio on the spot right there. I'm just happy he swung by to say hey. So everyone, give shout outs to Julio right there. And thank you for the positivity you bring. And I know you got to come in and see all the students and everything before everything went crazy in the start of 2020. And I know that means a lot to students because I've had students in my class who are like, I got to meet Julio for the baseball things. And they're like, yeah. What questions do you have? Thank you so much, Julio, for some guy. I really appreciate that. So what other questions? Covered a little bit so far. What other questions are there? If you are studying any sort of topic right now, let me know. Everyone give some congratulations to Julio right there. Like, we need to, like, everyone throw some congratulations out there. Graduating, that is awesome. Let's play, we're just going to play our 80s awesome music. Get some congratulations right there. Let's hop over to our time machine. Oh my gosh. I'm off the screen, everyone. Oh no. I grabbed the wrong thing. I got to grab the whole car. I can no longer do it. There we go. Julio, congratulations. We're going to do the list of formulas. Let's do it next here. Speedrun videos, they're on the channel. We'll make sure you get that link in the chat. Congratulations. Let's do this, everyone. Let's head over to the future right here. Let's do this right now. It's time to go. I'm ruining my effects. Lily, you got it. Here, we'll head back to the main screen. Okay. So Elizabeth said, do you have a list, like a list of the formulas and what they're used for? I get them mixed up. Yes. Let's make sure everyone knows where to find the review sheet or the formula sheet. The formula sheet is here. I'll send you the link in the chat in 2 seconds. 2 seconds, maybe we'll grab it. Here is where the Stat 2-1 review page is. And then we're going to do, Fletcher's got a question too. So that is where the review page is, and it has the official formula sheet. So it is pretty clear. I hope everything here is pretty well laid out. Start looking at this tonight. We can go over some parts of it next year. People have questions. Does that make sense, Elizabeth? Like, here's the formula sheet. You see here the 2 sample t-test as it's labeled, the 1 sample t-test. This is 1 sample t-test right here. This is for categorical data. So yeah. The previous question we just did use this equation right here with, whoops, not that one, sorry. Previous question we did use this one right here. We were doing the 1 sample t-test. And I see, can you go over nearly normal condition and chi-squared conditions? Yep. So that would be these down here, the nearly normal and the chi-squared. You do not need to memorize them. You can print this off. And here we'll put the speedrun link. I didn't put them in their own playlist. Sorry about that. I did not put the speedrun videos in their own playlist. If you go to the videos on our channel, they are the most, and I am knocking keys off my keyboard again. If you go to the videos on our channel, they are the most recent videos. Sorry about that. That's my fault. Hence why they're not getting that many views. It's my fault. So there's the link to the most recent videos and that. And you don't need to memorize the formulas. Once again, you can print this off, and this can be you can use this and 1 sheet of scratch paper to do your work. We've got Lily asking, can you go over the nearly normal and chi-squareds? Let's do that right here. I'm going to try later to go in and put some bookmarks in this video. I feel bad putting Lily on the spot. But no, congratulations. Graduation is awesome. That's just so awesome. Okay, let's talk about those conditions. So the nearly normal condition. Well, the first one we have is large enough n. And the large enough n is used for the sampling distribution of the sample mean. And the reason is because we can't actually see the distribution. So the way this works, step 1, check to see if the shape of the distribution. So the options are that it'll either be normal, skewed, or very skewed. So what we're talking about here is the parent population of it. And this is the large enough n. So maybe it looks something like this. How would you say this looks right here? How does the purple distribution look? So you'd say the purple distribution looks what? The purple distribution looks very what to me? You look at that and be like, oh, it looks pretty something right there. What does it look? Looks pretty normal. Great job. Hey, Bryce, good to see you here. Bryce, I think, are you this semester? I still get, see, we see. I love when just people swing by. And then now, we have to use the associated sample size. So with this right here, the more, and this is why it's called large enough n, because the more skewed it is, what do you notice? And I'll color code these right here. So if it's normal, then we only need this. If it's skewed, then we need this. Why do you think it's called large enough n? Why do you think we call it large enough n right here? Why is it called large enough n? Because the more skewed it is, the larger it needs to be. So it's not always 25 though. So in that previous one, if we were doing the sampling distribution of the sample mean of sample size like 5, we're fine because the original distribution is normal. And this deals with the central limit theorem right here, which states the sampling distribution of the sample mean will become more normal and tighter as n increases. So this is the more normal part of it, such that if we have something that is very skewed, would the distribution of the sample mean, like this distribution now is very skewed. But if we were to do the distribution of the sample mean of, let's say, sample size 100, how would it look? This is the single observations right here. So how would this look? Hey, Colin. Oh, Colin, you're the best. And congratulations. I hope, you didn't update me on it today, I don't think. Was it today? Wasn't it this morning? Did you have the final interview? So congratulations, Colin. I hope, I got my fingers crossed. So with this right here, everyone's just so positive. The distribution now, and this is because n is large enough, what does that mean? The sampling distribution of the sample mean is going to be normal enough. Yes, I hope to. Colin, I'm really hoping for you, man. Hoping for you right there. Keep your spirits high, man. You got this. Now, what is the nearly normal condition? It's kind of the same thing. This is used for, so all t-tests and intervals, which are 1/2. So a 2-sample t-test, a 1-sample t-test, a 2-sample t-interval, 1-sample t-interval. We always like to say Mr. T is mean if you're doing drugs, because the T is used for the mean. So when we talk about the nearly normal condition, there's 4 ways to check it. Look at the histogram. Does it look normal? Look at the normal quantile plot, or normal probability plot. Is it straight? Look at the goodness of fit tests. P-value greater than 0.05. And lastly, large enough n condition. So you can, this is why I combine them together a lot of times. You just can't use these for the other one. You can't use the large enough n when you can't see the distribution. But you can use the large enough n right here because the central limit still applies. The central limit theorem says it will become more normal. I thought, yeah, that's why I combine them together. I've always hated that we break them apart. It's just how large enough n works. It can be used in the nearly normal. So that's why you usually just put them together into one. And I really just hate that sometimes we use a little bit different wording. Like, it's important to know how large enough n works. And I usually just put them together. But this is why they are kind of separate ideas. But large enough n can be used to pass nearly normal. Does that make sense? So we're trying to get a distribution that looks more what when we're doing this right here. What is the whole goal of these distributions? That they look kind of what shape? The whole goal of this is that the distributions look what? And then we'll actually look at the large enough n right here in a second. So the whole goal is that these distributions don't look this, they look this. The whole goal is that they look normal, exactly. So when we're talking about the large enough n right here, I think we've got, here we go. So here's what we would do. We would look at this right here, wrong button. We'd go to analyze distribution, and we would do something like people's high school GPA, and we'd take a look. And, you know, for the most part, what issue might this have? Like, it's not that bad. I mean, I see a little something over here. What do you think? Does this look like it would pass the nearly normal, yes or no? What do you think? Does it pass the nearly normal? It is slightly skewed, I would say. So this is where actually I would go straight to the large enough n, and I'd say, well, it's a little bit skewed, but the sample size here is 806, which is a very high sample size, which means that the distribution of the mean, which is what we're interested in, will be nearly normal. So it's pretty normal to begin with. It's not too crazy, and the sample size here is pretty large. So the steps are kind of, I hate to say this, like this is a much more complex issue, and I've kind of alluded to some help for the test. is that how do we not check this? How do we not check this condition? Like, I don't like to give away test questions, but how do we not check this condition? How do we not check it? Like, we can look at the histogram and be like, histogram looks pretty good. We can look at the normal quantile plot right there, normal probability plot, and be like, it's pretty straight, which is good. We can look at the p-value for the goodness of fit test, and that's probably going to be low. We can look, it's a continuous fit. Where's continuous fit? There it is. Fit the normal. It's not going to pass. It's not going to pass. Where's the goodness fit? There it is. Yeah, it doesn't pass. I'd have been shocked if it passed. Don't use bar charts. People know that right there. Not that I'm telling you something, but don't use bar charts. Bar charts are for categorical data. For the most part, I would say this is pretty good, especially since we're talking about the distribution of the mean. Just knowing these things right here. I just went through all 4 of them right here where we look at the histogram, a little bit of a skew, a little bit of outliers. We look at the normal probability plot, pretty straight. There is an issue with the goodness of fit test right here because the p-value is low, saying we reject. So that everything right there is going to tell you we reject normality. But we're talking about the distribution of the mean, so the sample size of 806 is pretty good. Once again, I'm going to repeat this again just so you can see I'm talking about all of these steps right here. Step 1, here, let's take the, Step 1, look at the histogram. So when you look at the histogram right here, say, hey, that histogram looks pretty good, looks pretty unimodal symmetric. Step 2, we look at the normal quantile plot or the normal probability plot. I look at this and I say, hey, that's pretty straight. Straight means it follows the normal. It's trying to see, does it follow this? And yeah, that red line down the center is the normal. Not horrible. The only one we have a bad thing on right here is this over here. And we say doesn't look too great because the p-value is low. Low p-value indicates lack of normality. So the p-value is not greater than this. That's a problem. And then the last one is the large enough n right here, which we actually do well on that. So I'd say we're pretty good on this. There's a lot of, like, this is a big topic, especially like distributions in statistics. I think the next question was about chi-squared. So let's talk about conditions for chi-squared right here. We've got our really good cheat sheet. I hope everyone's been seeing this good cheat sheet, like for the conditions. Has anyone used this and they feel like they understand the conditions because of this? It's something new I made this semester to kind of do this step by step when you're checking conditions. But who feels like they use this sheet right here that we made and they understand the conditions now? Like, does anyone like, yeah, I got it down. I practiced this right here, Brian. That helps me understand the conditions. I know what you're talking about when you do this right here. When you do condition 1, randomly sample. How do Applix works for the exams? We give you a lot of pictures right there, Caleb. So we'll give you pictures or we could give you jump output. Great question. So pictures or jump output of pictures of the applet or jump output. So condition 1 is randomly sample. So we randomly sample the observations. Condition 2 is that we sample less than 10% of the population. Condition 3 is where we pause. Don't just like rapid fire to condition 3, because if we're doing a 1 proportion Z test, what would be condition 3? I'll give you some rapid fire questions here. You ready? So tell me which condition 3 we're talking about. Brian goes out and asks people, do they own a dog, and wants to make a confidence roll to figure out the true proportion of students who own a dog. So what condition 3? See if you can get it, and I will circle it. Brian wants to figure out, do students own a dog? What is condition 3? Success failure. Got to pause for those dogs. And there's no condition 4. That's why I've color-coded it right there. You would stop. That's just one variable. If you have 2 variables, there is a condition 4. It's categorical, success failure. Excellent work right there. Brian asks students if they own a dog and are they married? So we want to see, do you own a dog, and if that's associated with being married. Like maybe married people are more likely to own a dog. Who knows what condition 3 would be now? So think what we have right here. Oh, you could, Aaron. We could do some of those questions next where you have to find p-values of sorts. Expected cell count, which means the expected cell counts need to be all greater than 5. So expected cell count is expected cell count greater than 5, and that is the condition here. And notice the color coding. We have count data, which means owning a dog and are you married or what kind of questions. Ben's putting some good stuff in the chat right there. And so Ben's kind of answered the question like owning a dog and are you married are what types of questions. By saying count data, we're saying, oh, they're both this. Like to have count data, which means you're doing, that's your 3rd condition, that's your 4th. There are no orders to these. I just think it helps when you do them in an order like this. The 4th condition here, count data, means owning a dog and are you married is what kind of data. Both of them, which Ben's alluded to, both of them are what kind of data, which is what count data means. Count data means both variables are categorical variables. Nice stuff, Fletcher, right there. Yep. Both variables are categorical. What could I could ask people dog owning again, dog, and I could ask people what other question. I need to ask a second question, or I could, well, to do this one, what else would I need to ask? Like, do you own a dog? Yes or no? And then I'd have to ask them another question to actually do this right here. So do you own a dog and what else? I could look at the differences between people who own a dog and don't own a dog and the differences in their what. So people who own a dog, what's your GPA exactly? That's a quantitative question. So that's really the big important thing right here is we're dealing with a quantitative Y right here. That's where the nearly normal comes into play. You could ask GPA, but if you're doing GPA versus dog owning, yes, no, then you've got here the two groups, which is the independent means. This is where you could ask like, so you could ask, well, no, you could, Amelia, I like that one right there. You could ask, oh wait, no, is it, Fletcher said, you could ask people how many pets they own and do they own a dog. So you could see if people who own dogs own more pets. So you could do number of pets and you could just do a one sample t-test or one sample t-interval. And this would just be how many pets do you own? But then you could see if dog owners, like when we go to like, do you own a dog? Yes or no, dog yes, and dog no. We could see if people who own dogs own more pets than people who don't own dogs. Does that make sense? Ask them if they feel stressed. Yeah, that's a good. Yeah, that'd be categorical. We could say, you know, like we could ask people their stress level and do you own a pet? So now the question is like we could ask people stress rating. So like rate your stress level 1 to 10 and do you own a dog, yes or no? So we could ask this right here, like how, so we could try to do research to say like people who own dogs report on average less stress. Does that make sense? Independent groups or independent means independent groups means that people who own dogs stress levels is not impacting people who don't own dogs stress levels. So we don't have to do a 2-sample t-test. We could just ask people what their stress rating is and say, here's the average stress rating that, you know, this group reports. Or we could say, you know, let's compare the stress rating for people who own dogs and don't own dogs. Now, the main variable of interest in all of this is stress rating. We're trying to understand stress rating. And then the explanatory variable down here for the 2-sample t-test is going to be dog versus not dog exactly. And so Ben is pointing out perfectly that this variable right here is categorical because you have two groups, and that's what creates the two means right there. So that's the 2-sample t-test. What time is the review? Tomorrow? Maybe review tomorrow. Can't promise I'll review tomorrow. I might be answering emails or getting this review tonight. I don't know. I was like, I'll hop on a review tonight. Definitely, I would say I probably won't review tomorrow. I would be watching the videos. So probably my biggest suggestion to you, is it what I say from the title? I can't even remember. Night before Stats 1. Oh, it's the night before Stats 201 review session. I'm not that good with titles. I think there was another question about finding p-values, wasn't there? Like finding p-values in output. And let me put this video list in the chat. So if you're watching this right now, I would watch this test 3. Where'd I find it? Where'd I go? Test 3 playlist review. And I'm going to put it to the video I would start on. Understanding which test to use and when is very important. And no worries, Joshua. There's the playlist. The exam opens at 1. It actually opens at, I think, 12:45. We opened it a tiny bit early, not to create conflicts for anybody, but just in case there's issues. So we have it open at 12:45. Is that correct? I believe so. I can go look at it. Let me confirm. I'm always afraid to like say things and be wrong. Okay, I'm taking a look over here. The exam opens, and please email us immediately if you have any issues. 12:45 to 3:30. It is, we just extend the times a little bit around it just in case anyone has an issue with logging on. It officially opens at 1. It goes till 3:15, I believe, officially due to university timing. But we did a 15-minute window around it just in case anyone wants to start early and just in case anyone has a little bit of trouble like logging into it. Make sure to reserve 90 minutes. Canvas just says when it closes, it should say 3:30. So 2:45 it opens. Or 12. Oh my gosh, 12:45 it opens. That is correct right there. Great question, Elizabeth. Hop here to space. Was it? I think there was another question about p-values. Was there? People want to talk about how to find p-values. And definitely, I know some. Let's go find some p-values. Thank you, Lauren. Lauren is correct right there. Let's find some p-values. Okay, let's hop over here. So let's talk about jump output a little bit and understanding how to find p-values. Do you think who spends more on pets? Let's find out who spends more on pets. People in Greek life or people non-Greek life? Who do you think spends more on pets? People in Greek life, yes, or people in Greek life, no? So we've got here Greek life, and what kind of test is Brian doing by analyzing who spends more on pets? We've got here pet expense, we've got here Greek life. Who spends more on pets? What kind of test am I doing? So I'm asking, are you in Greek life? Yes, no. Oh, Serena, so good to see you here. Yes. Serena, did we interview you? Because I believe me, like UT and everyone, like for those with the students we interviewed, like the people who've seen the interviews from the students are like, they're just like astounded by it that the students really love this class. And thank you so much, Serena. It's so good to see you in the chat again. We got Mubot here now. We got a lot of new additions. We got Tiny Brian.
I'm Tiny Brian.
Oh, no worries. It was the first group of students. We actually did interviews with them. I do remember your name in the chat. Oh, look at this. That's a skewed distribution. I like when people swing by and there's like, oh, it's so good to see people. Do you think non-Greek life has more pets? Let's find out. There is it is, which group does have more pets? Wait, the difference is, oh, how much they spend on pets. I was like, that's not. So which group spends more on pets? Let's isolate this so we only see it. Which group spends more on pets? Who can tell from this output which group spends more on pets? Who can tell from this output which group spends more on pets? Let's look at this. Can you tell? Is it the people in Greek life or the people not in Greek life? Who spends more on pets? So we see here the difference, and you can always put right here that you're analyzing the difference between the mean of yes and the mean of no. So which of those means was higher? Who spends more on pets? Who spends more on pets? Don't look at the other answers. About to blank them out. Who spends more on pets? Is it the yes group or the no group? Sure. No, it looks bad. The colors, they just don't. It is the yes Greek life. The reason being is because this number here is positive, which indicates to you that the first mean is higher because you're doing a big number minus a small number. Like imagine if I were to say $10 minus $4. Would that be a positive or negative difference? That's what you're doing right here by doing yes minus no and the difference being positive. The positive number indicates that the first sample mean, so this is actually the sample difference, mean 1 minus mean 2, the first sample mean was higher. Now we're trying to understand the true difference right here. So that's the null hypothesis, is that there is no difference between these. So the null hypothesis, which you can also see here with this value, we are hypothesizing that the true difference is 0. Is it cool if I write the formula? You are allowed to do that if you don't have a printer. Yep. Just make sure you only write the formula, show your formula sheet, just make it nice and clear. Be like, here's my formula sheet. I wrote it down. Thank you there, Lauren, for that question. Great question. So make it very clear when you show up. Be like, here's my formula sheet. And just, yeah. If you're like, here's my formula sheet, just make sure to show everything nice and clear. We don't like, just be like, pretend you were watching, like, someone had to check it to make sure or anything. Like, just don't be like, just like, formula sheet, boom. There you go. So thank you, everyone, for 99%, maybe 90%. 90% of people do a great job of doing environment checks. And if there's ever a question, like, and we only, like, the way it works, if you're wondering from the back end how it looks, the respondus shows us, like, if there's, like, alerts and stuff like that, because trust me, I'm not going to watch 2 hours of everyone taking a test or 90 minutes of everyone taking a test. But we go in and look at the high alert stuff. And so usually it's just someone like this, like somebody just like with their head down, and then it's like respondus does not, it's like they left the screen and you're like, they just put their head down. That's like 90% of the alerts. So try to, it's gotta be tiring. I can't imagine. I haven't gone through what everyone's going through. So I can't empathize with you, but I do try to sympathize, and thank you for everyone who does it. I appreciate it. So with this right here, let's look at these p-values. How can we find these p-values if they were missing from the output? So what test do we have right here? What test do we have right here? What test do we have? We actually have the what then test. That's where the T landed. And we actually have the what then test. What test do we have right here? Great job, David's finding the greater than test. Exactly. The greater than test is right here. And we know the less than the greater than add up to 1. And this is a difference between two means test. Yep. And so I guess, ooh, great job, Fletcher, right there. That's the test. I should have said the alternative. And that's the less than alternative. So I did misspeak. Fletcher, that's where the 100 points for everybody. So Fletcher is right. This is the difference between two means test, also known as a two-sample t-test. And we're talking about the alternative. This is the less than alternative, which means we shade to the left. That means, if you think about what does this all mean right here, 90, I'm clicking on buttons, 97.09% of the area is to the right of that green line. To the left, I can't speak. To the left of that green line. So David went and found us this p-value right here. Whoop. How do we find this p-value? We just do 1 minus. So we're going to take the p-value right here, the less than, the greater than, add up to 1. So we do 1 minus this right here. And that's that p-value. And once you get this one, what are you going to do to find your two-tailed one? The two-tailed p-value, so this is the two-tailed one up here. Right here is the two-tailed. What are you going to do? Kyle, great job, Kyle. You're 100% right. The two-tailed, and you can see it here visually. Here is the greater than alternative. Look how this points to the right here. So that's the greater than p-value. And then the two-tailed is just double it. So literally, and sometimes the jump output can look a little different. We got lucky. The reason being is jump carries more decimals in the background. So great job, everyone, practicing right there, knowing that this is double. Because here is basically 3%, and here's 6%, and here's 97%. I wish the numbers had been super nice, but 3%, 6% total on both sides, and 97% below here. So really good practice on that. Another important thing to know is that when you're finding this t statistic, especially in this output right here, you're going to be dividing these two numbers. And if you look, it's basically 200 over 100. Basically. So it's about 2 right there. All that good stuff. What other questions are there? Let's try to take a few more questions. Might go till about 10 your time. Definitely check out the videos. Ask questions if you have them. I don't know if I'll read them. What questions are there? This is your time to ask questions. What are you wondering about? What are you stuck on? It's over here. Space. Is it always it's always double the smaller one. It's always double the smaller one. Great question right there. So Aaron, and let's show that again real quick right here. It's always double the smaller one because p-values have to be between 0 and 1. So it's not always double the greater than. It'll always be double the smallest. So whatever your smaller of the two p-value is, does that make sense right here? Whatever the smaller of the two numbers is, you double that and you get the two-tailed. It's basically because it's a reflection. This is the 3%. Here, I'll highlight what I'm talking about. This right here is that area right there that I'm pointing at. That's 3%. So what you do then is you double it and you bring it over to the other side, and that's how you're getting, so you're doubling it right here. You're taking this and reflecting it and getting 6%. Does that make more sense, Jesse? So whichever side it's on, it doesn't matter if it's left or right side, left tail, right tail, less than, greater than, you'll just double it to the other side. So it's instead of 3%, 6%. Great. You're welcome, Aaron. So the probability value, and that is going to be the does not equals test. So this is the two-tailed. So that is specifically, just to point out which one it is, I'll highlight which one I'm talking about as I do this. This p-value represents this area right here. That's the two-tailed does not equals test. Zoom out just a tiny bit. And this p-value right here represents the greater than the green line. And the green line is our test statistic right here. That's the t statistic right here. That's the t right there. And this last p-value, the less than, is less than the green line. It says less than t. So you shade less than t right there. It's not actually shaded because it would take up too much of the curve. But that's less than it. So it's everything below that green line right there. You'd go below that green line. It says like probability less than the t value you observe. So you go to the t and you shade to the left of it. Yep, it says Elizabeth Siskin shows her. I think, did Emma have a question? What's the best way to determine which equations to use and when? Just make a chart. The best way to do it is always to identify. Here, we'll do a test question here, Emma, to figure out what is the notation. So always write down the notation. Let's do a test question here, and then Elizabeth's question is next. Let's do this. Okay. So here is the test question. And the test question is going to be, Brian takes a sample of 100 random UT students. That's all I ever do. He asks them, do they like Hard Knocks Pizza, please sponsor us. I'm just kidding. They don't gotta sponsor us. Surprisingly, only 70 say it is awesome. He wants to know if this is evidence that more than 50% like Hard Knocks Pizza. Okay, so what test? Let's say what notation first. That'll help us out. What notation? What test? Run the results. Okay. Okay. So here we go. And so did it depends on the alternative. I think so. Great job answering each other's. And I think this will help right here. So this should help Elizabeth also. Can you show the chart again from the conveyor with what to use and what variables? Yep, I think so. Yep, I'll show that here again, Elizabeth, in a moment. I forgot what it's called. I think it's my all variables thing. So who knows what is the notation? What is the notation? So Ben, be careful. Remember, Mr. T is what? Mr. T is what? So double check. You got the one sample right, or you can just call it. So Mr. T is what though? Mm-hmm. And we'd probably call it the big thing to make sure we know about this. So David, I think you are correct. And so what do you notice we're analyzing right here? What kind of variable? And if you get the notation, you're fine. Like, I'll show the formula. Correct. Mr. T is mean, and I don't see any means right here. I don't see any means. 1 proportion Z. Exactly, Jesse. Great job. So this is a 1 proportion Z right here. Identify the notation. See if you can put it in the chat. Once again, the more you write these down, if you're writing this down while I'm doing this right here and identifying the notation, and it's categorical. Great job, Ben, right here. So it's categorical, so it's not means. This is all practice. Don't worry. We're here to practice. So what do we have right here? What do we have? We are going to identify the notation. What do we have? So we have here N. Great job, Fletcher, right there. Yes, so no, P hat. You are on the right track, and you can probably figure out P hat from this. So that's P naught. That is the hypothesized. So T is mean and Z is proportion. Pretty much only. So Crystal, that's the way I like to memorize it right there. Like Mr. T is mean if you're doing drugs. So T mean, and that's for a 1 sample T test, 1 sample T interval, 2 sample T test, 2 sample T interval. There's the one exception. I just want to show that really briefly right here. The one exception is up here for this. For the sampling distribution, we do use Z. And so all the T tests right here are means. So if you do hear T test, you are doing stuff with means. Oh, that's not the T test. Here's the T test. So here's the T test. That's a mean. There's the T test. There's the T interval. And these are all means right here. But usually a lot of times when we're doing Z, we're doing proportions. But there is the one instance up here of the sampling distribution. The formula sheet does show it though. So good stuff right there. P hat is close. Yes, Ben, you got it. Great job, Ben, right there. This is actually X, but as long as you know that you're going to do 70 over 100 equals P hat. So P hat is equal to 0.70. That's the proportion of students who said they like Hard Knocks Pizza. And this is sample size. And we can run the test. I got the notation. What is the test? 1 proportion Z test. The formula for this is going to be P hat minus P naught over P naught Q naught over N square root equals to 0.70 minus 0.50 over, this is going to be 0.5 times 0.5. Nice right there. Over 100. It's always 100 in my problems. And then we go right here. Okay, let's solve this. So solve the Z with me right here. Let's see. So I started writing the test right there. So it's a 20% difference up top. That's right there. Divide by 100 square root. And that's going to be a Z statistic of 4. Did anyone else get anything different? Z statistic of 4. So this would be one where we could actually tell you, will you give the Z the T for the confidence interval? Yes, exactly, John. Yep. We always give the Z and the T for the confidence intervals. Great question, John. We could do one of those next. I could do like a ZET confidence interval. And so this right here was equal to 4. And this one right here, we could ask you if you fail to reject or reject the null. So what do people think? Do you reject the null or fail to reject the null? This one right here is, Brian was wondering if more than 50% like Hard Knocks Pizza. So the alternative, because I asked more than, is going to be greater than 50%. And I can get to the p-value pretty close in my head, hopefully. So we're asking if more than. So the more than right here. Definitely reject the null. Q naught. Yes, exactly. Great job right there, Theodore. Thank you, Theodore. Excellent work right there. I forgot to identify that this is Q naught, and P naught and Q naught add up to 1. So great job, Theodore, right there. Does that mean it's 4 standard deviations above the mean? Exactly, Ben. And does that sound very unusual to you? To say something is 4 standard deviations above the mean. This was step number 2 of hypothesis testing. Find the Z or the T. And so that is the Z right there. And so now we're going to draw out our curve. And just knowing that it's 4 standard deviations above, we're talking about a p-value, which I have to disappear for you to see. The p-value is this. The p-value is basically unobservable. So we're going to look at some David M. Lane right here, but maybe the question would say something like, which of these p-values seems most reasonable? So it could say A, 0. I'm trying to think of it. This is going to be the right answer. 0. It's going to be so small, it's going to barely show up. B, C, I wouldn't make it. I think this would be a very, very fair question. Really? Sure. Those are your 3 options. Just drawing this out right here, it should be pretty clear. Word just doesn't like me. So let's go ahead and check the David M. Lane and look at this. We got a z-score of 4. So we're going to go above a z-score of 4, and we should get a p-value. It's basically 0. We'd actually have to use R. What am I doing in R lately? 2 seconds. Not class over yet. What have I... Oh, I got R on the other screen. 2 seconds. Because I actually want to look at the p-value here. Class is over screen. A is seeming... Yeah, exactly. And so it's Z... Wait, Q norm. You don't have to know how to do this. I want P norm. And this is the area below it. Yeah, this is the area above it. Yeah, it's ridiculously tiny. It's 0.0000 and then 321 or something. Yeah, it's very tiny. So that's why this applet right here is just basically, you can't even see it. My drawing is not even good enough right here. So this question was asking about the confidence interval. Would we use p hat? So now, great question right here. Crystal, let's switch it to a very similar type question. You won't use this Z right there. You'll do it different. Let's say now, great question, Crystal. Now Brian wants to create a confidence interval for the true proportion of students who love Hard Knocks, because Hard Knocks is awesome. Shouts to Hard Knocks Pizza. First thing Chelsea and I are doing when we get back to Knoxville is Hard Knocks Pizza. So we're going to go right here and go p hat plus or minus, and the star is very important right here because the star means we get to pick the Z based on our level of confidence. And I believe this is on the previous exam. It's a good tangential question. And what we would do right here is we would say use Z equals 1.96 to create a 95% confidence interval. And so does that make sense to everybody right here? We'd say use Z equal to this to create a 95% confidence interval. Exactly. We would give you the Z. That's important. I'm not going to really solve this one because I'm pretty sure this is on the last exam, because this one we start with like confidence intervals for the mean and sampling distribution of the mean, and we have this on the last exam. So this is chapter 13. They changed like the chapters in the book. It makes it so confusing. But we will give you this right here, and then you would plug in and solve. So the solve for this right here would be, we would just take and plug in p hat is 0.7, q hat is 0.3, 100 sample size, 1.96, and then 0.7 right here, and then you would solve. So just plugging in numbers, solving for the confidence interval would give you, I am 95% confident the true proportion of students who like Hard Knocks Pizza or love Hard Knocks Pizza is contained in the interval. And there it is, about 9%. So it'd be, we're just going to round that for the time being, 61%. And I did want to do this right here because I want you to notice something. What do you notice is not in this interval? what value that we started out looking at is not inside this interval? Because we just did what to it a moment ago. What value that we started off at the very beginning talking about is not inside this interval? 50%. So 50% was a value we rejected, and now we're saying, well, yeah, because I'm 95% confident the true proportion of students who love Hard Knocks Pizza is 61 to 79%. So I reject 50%. I don't think 50% is true. I have good evidence against 50% being the true proportion of students who love Hard Knocks Pizza. What other questions are there? And that's a good kind of, thing to mention right here is that when we do a two-sided test, which we didn't technically do the test. We could have done the two-sided. When you do a two-sided test, it's the same. There's the two-sided test. If you use an alpha of 0.05, it's the same thing as doing a 95% confidence interval. This one we rejected at a very high rate, so we would still reject it with the two-tailed test on the other one. We could switch it. We'll go to David M. Lane. We'll say give us the two-tailed. So we want to go outside of this, -4 and 4, and the p-value is 0.00001. Very, 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 very tiny p-value. What additional questions are there? We'll go for like 20 more minutes. Also, so get to alpha would do exactly perfect answer right there, Crystal. Great job. And that's what we're doing right here is the respective confidence interval that can do your two-tailed test would be 1 minus alpha. So great notes right there, Crystal. Great job. Is that all we're doing is just 1 minus alpha right here equals the confidence level of the test, like the respective confidence interval that would do the two-tailed test with an alpha level of that, 1 minus alpha. Could you go over type 1 and type 2? Yeah, let's do some type 1, type 2. Now, the biggest thing is you got to remember the shortcuts. I'll try to put that. I got to remember, it's my new thing this semester, putting cuts, and it's helped me so much labeling videos. Let's do this. Type 1, type 2 error. Okay, here we are with some type 1, type 2 error. Okay. Type 1 error. In a type 1 error, it is the null is true and we reject it. Okay, let's talk about this. You've got a cheat sheet right here. You've got a cheat sheet with your hands because all you have to do is hold up the 1 and say in a type 1, the null, and I'm holding this up right here, the null, not that one, the null is true. In a type 1, the null is true. Does that make sense? In a type 1, the null is true. Type 1, null is true, and we reject it. In a type 1, a lot of times they do it with just the I. In a type 1, the null is true, and we reject it. In a type 2, we're just talking about how to memorize these right now. Then we're talking about some context on these for a moment. I think I see a question from Ben next. So in a type 2, the null is false, and we fail to reject it. Okay, so let's take a look at this right here, and you're going to see me do this right here. So here we are. In a type 2, holding up 2 fingers right here, the null is false, and we fail to reject it. So you have to do it twice for the type 2. In a type 1, the null is true, and we reject it. In a type 2, the null is false, and we fail to reject it. So what does this mean in context of the problem? Who wants to say something they like? Maybe it's video games. Maybe it's, I don't know, dogs, horses, whatever you like. We'll go with that as the example. Maybe it's, I don't know, biking. What do you like? Maybe it's pizza. What should we use as the example and like come up with a type 1, type 2 error example? We can talk about like, what is the type 1, type 2 error in context of this problem? Ben, if you expand it. I like dolphins. Dolphins are cool. So let's say you're trying to see how long it takes. Like you're trying to train dolphins. So are you saying like training dolphins? Is that like, I don't know, God, all these topics. So let's say you're trying to teach dolphins how to do tricks. Does that make sense? You're trying to train them to do tricks. And so with this right here, you've got the null hypothesis would be, oh my God. You got the null hypothesis right here. Sure, perfect. Thank you. Awesome. Null hypothesis is continue current way. The alternative is use new way. And so think about this. If you've been doing this for like years, you without evidence, you would just continue to do what you're doing. Does that make sense? Like people are going to do what they always have been doing unless you provide them evidence like the new way would be better. So someone says to you, hey, we've got this new way, this new training method. It's really going to be quicker for them to learn. You know, they're going to be doing the tricks better, like, and it's just all around better. And you're like, oh, that's interesting. But you would say to them, I need what to use the new way? Like, you're going to have to show me some what if I'm going to use the new way. I think it's an alternative, so it's the what-based claim. So if you're like, well, I use this old way, and it's kind of what I believe is the best way currently. It's my currently held belief. It's my null hypothesis. I'm going to need you to show me some what that this is a better way, some evidence. Exactly. That's what the alternative is. It's like, well, I mean, if you can show me good reason to believe it's better, then I'll believe it. And if it's like way better, effect size, that'd be easy to see. But if it's a little bit better, that might be hard to see. So when you think about a type 1 error right here, reason to reject the null, some good evidence. What was your example of the cheaters? Oh, we can do that one next, John, if you want. We'll do the cheater example here, and then we'll see if people can get it. So we'll do this one, and then we'll do a review with the cheater example to see if you have it down. So I want you to look at this null hypothesis right here in a type 1 error. I want you to look at it. There it is right there. And I want you to say this is true. What does that mean? Like, think about a type 1 error. Let's look at this like it's a type 1 error right now. Like we make a type 1 error by doing this. This is true. So this is true. So this is what we should do. This is true. But what are we going to do to it? And what does that mean? We decide. Like, I want you to fully explain the context of this, of making a type 1 error. This is true in a type 1. In a type 1, the null is true. You have to look at the null and say, that is true. And we are going to reject it. Exactly, Theodore, exactly. We're going to reject using the current method. And so what are we doing right here? Like, tell me in context. The null tells the truth. Yep. The current way is best, but we use the new way. That's exactly, David put it correctly right there. The current way is best. Like, it is true that we should continue to use the current way. Using is actually better, but we say the new way is actually better. Exactly. So we're making a wrong decision right here. We say, there's evidence, false positive, that the new way is better. We're rejecting the true null. Reject, but use the new way. Exactly. We reject to use the current way. We're like, there's evidence to use the new way, but we shouldn't. So let me slow it down. I think a lot of people are getting it. I'm worried someone watching this might not be. In a type 1, the null is what? Look at this. Just slow your brain down. That's what I have to do myself. You look at that and you say, that is true. We should do this. That is true. But I'm rejecting this. I'm making an error. That's an error, type 1 error. And I'm going to say we should do this. So we are going to use the new way when we shouldn't. Now, what would a type 2 error be? In a type 2 error, the null is false. So remember, type 2, the null is false. There's the F right there. And we fail to reject it. So this is false right here. What does that mean? If this is false, what does that mean is best? We should do what? If this is a false statement. So in a type 2 error, this is a false statement. So think about the context here. I can always say the answers, but I always want people's wheels to start spinning and be like, okay, wait, that is a false statement. David put it perfectly. Exactly. So the new way is better, but we use the current. Exactly. We should use the new way. But what are we going to do to this? Because that's the correct idea. Like, this is false. The current way is like false. We shouldn't be doing that, but we are going to fail to reject it. We shouldn't be using the current way, but we still do. Elizabeth, that's worth 100 points for everyone. Thank you, Elizabeth. I'm hoping it's starting to make more sense. You have to look at these and then use it. So we do the cheater example as a classic one. So the null hypothesis is not cheating. And the alternative I need evidence for is cheating. So when you think about this right here with the cheating example, what is a type 1 error? I just want you to look at me and say, Brian, it is true they did this. Don't tell me the full example yet. Just do a type 1 error right now, and I want you to say, Brian, it is true this. Don't do the full thing. Just look at it and say it's true about this. I want you to look at the thing and say, hey, Brian, it's true this. This is true. Don't do the full thing yet. And then I want you to think about the error we're going to make afterwards. I want you to say, Brian, it is true this. Type 1 error right here. Brian, it is true that this. Brian, it is true this. This is a true statement. What is the type 1 error right here? Oh, be careful, careful. Remember, the null is true. It's true. Well, it's not that. So we're saying like we're talking like a student. We're saying did they cheat or not? It is true that they were not cheating. Does that make sense? You look at the null and you say that is a true statement. You just look right at the null hypothesis. And you say that's a true statement. Does that make sense right here? We'll do one more test too. Great job like this. I think you caught it. Yeah, it's true that they did not cheat. But what are you going to do to that null? Type 1 error right here. What are you going to do to that null? So it's a type 1 error. What are you going to do to that null? Got the cheat sheet up here. In a type 1 error, the null is true, but we reject it. It is true that they did not cheat, but we say they cheated because we're going to say there's evidence of cheating. It's type 1. Type 2 error, I want you to look at this null hypothesis, and I want you to say it's what? I want you to say, you can say, it is blank that they blank blank. People are getting it. They're getting the type 1, type 2 right here. I want you to look at that null hypothesis and say, it is a false thing that they blank blank. So just do the first part. It is a false statement. So the null is false. Whatever that null is, it's a false statement. That is not true. It's false that they are not cheating. And I think Megan's getting it right there. Megan, you are correct. It is false that they are not cheating. So in the type 2, they actually did cheat. It is false that they are not cheating. So Elizabeth, you are correct. They did cheat it because it's false that they're not cheating. It's like, wait, it's false they're not. It is false that you did not cheat. You're like, what are you saying? I'm saying you cheated. Can you talk normal, Brian? It is false that they are not cheating. They did cheat, but you're going to make an error. So think about what error you would make if someone cheated. You would fail to reject the null. By failing to reject the null, you're saying, I don't have enough evidence. Does that make sense? I'm like, well, I don't have enough evidence. I'm going to fail to reject the null. So someone would get away with cheating right here in a type 2 error. So I think we said we're going to do one more. I'll do a context example. Imagine a company is doing a pizza deal. And we have right here Mu. They want to know if, on average, these coupons are making them 50. Now, let's say, on average, they're making an extra $5,000 a week. They want to know they want to make at least $5,000 a week with these pizza deal coupons. Okay. So imagine this. A company like Hard Knocks has a pizza deal coupon, and they want to say, on average, like we see an average increase of more than $5,000 to like keep doing this pizza deal because they have to send people out to do it. And they'd say, okay, it's worth it if we make $5,000. Like if there's evidence that this deal is making us greater than $5,000. Who understands this example right here? Like Hard Knocks is doing some sort of statistical test to see if they're making at least $5,000 by running this pizza deal. And they're going to like continue running the pizza deal if they're making at least $5,000. So they're saying like, is there evidence we're making more than $5,000 by doing this deal, like weekly deal that they're doing? I don't know what the pizza deal is. So I actually kind of want to know. So with this, what is a type 1 error? So when you think about this, in a type 1 error, the null is true. But they're going to reject it and say what? So what would happen in a type 1 error? What is Hard Knocks going to decide to do? This is the more complex one. It's a good business example. Hard Knocks in a type 1 error is going to do what? This is the more complex one. In a type 1 error, Hard Knocks is going to decide to do what? Remember, the null is true, but they're going to reject that. So what are they going to do? Who could explain this to a business? Well, if you make a type 1 error, you're probably going to do what with your pizza deal? Are they going to stop it? Are they continue it? What are they going to do right here? Because they're looking for evidence that it's making more than $5,000 to probably continue it. So Hard Knocks is saying, does this pizza deal make us more than $5,000 a week? Dawson, you're exactly correct. They're going to decide that the deal is worth it because they're going to reject the null. Remember, the null is true. In a type 1, the null is true. I'll highlight what we're talking about. In a type 1, the null is true, but they're going to reject it. And they're going to say there's evidence that they're making more than $5,000 when they're not. So they're going to be like, hey, this is the best pizza deal we've ever had. There's good evidence. Like, we're going to say that we have the evidence. Does that make sense right there, Dawson? That they're saying they reject the null. They have evidence for the alternative that they're making more than $5,000. Type 1 would be saying they make more than $5,000 when they really don't. Exactly, Fletcher. So they're going to do this pizza deal when they probably shouldn't because they're not making the money they want. So it's going to be a bad business decision. So in type 1, they make a bad business decision. So type 2 is going to be what now? In a type 2, the null is false. So the null here is false now. It is a false statement that the null is false. And I mean, the null is false. And they're going to fail to reject it. So what's going to happen? Like, what would you say to a company about making a type 2 error right here? You'd say, well, then you whatted on an opportunity because the null is false. So the alternative is true. They will make more than $5,000 a week on average. Like the null is false. The alternative is true. I try not to say true because we talk about true with the null. But the null is false in the type 2, so the alternative is true. Type 2 would be they would stop the deal when they don't. Exactly, Fletcher. Exactly. Type 2 is going to be that they're missing out on an opportunity right here because they're going to, the null is false. They could actually make the money, but they're going to fail to reject the null right there. They're going to say, well, we don't have enough evidence. So they're going to miss out on making money. So you might think about type 1 is more risky for businesses where type 2 is like playing it safe, at least in this scenario right here, because it's all scenario based. Neither of them are the worst one. It's all scenario based for business. Type 2, they're making more than 5,000, but they fail to reject the null, so they miss out on making money. Amelia, perfectly put. That is how we would explain it to a business, and that's kind of what I like about business analytics. Not trying to shout out business analytics. They more than 5, yeah, exactly, Elizabeth. Great job, answer, Elizabeth, right there too. Who wants to do one more topic, and what questions do you have? We've been streaming for a while right here, and the stream's been good. How many people do we got watching? Got 44 people watching. That's awesome. What other questions are there? Thank you, everyone who swung by with questions. I really appreciate it. Let's give out some 100 points. Get Grace over to those bonus points. What is power? Power is the ability to correctly reject the false null. So when you have a powerful test, like the literal definition of power is, I'll write it here in the chat, or I'll write it down here somewhere. Sure, right up here. Power is literally, so, and it's 1 minus beta mathematically. So power is equal to the ability to correctly reject the false null hypothesis. So just kind of speaking about why we have power, if you don't have a powerful test, there's no reason in running the test. It's like saying, let's take 3 samples and see if we find results. You'd say like, well, that's just a waste of time and money. So a lot of businesses really care about doing it. We'll do a chi-squared. That'd be a good thing to end with, Alexander. We'll do a chi-squared one. Is there a big idea from the business analytics? I think the review I did, so check out the speedrun on that, Kyle. I think the review hits upon all the big ideas, and we had a little bit of fun talking about Disney and stuff. So definitely if you watch the 25-minute speedrun review of it, pretty sure I cover everything major. Like, I don't know, I need to look over the questions. I think I covered everything major. I don't like for like topical stuff like that. It's kind of like I just want to kind of say what you need to know. And we're not trying to make those hard questions. It basically, if you paid attention to like us talking about Target and Moneyball, you should be good on the business analytics lecture. You should be good. So just yeah. Can you go over that? Oh, the chart. Is it? Yeah. Let me go grab. I think I know what you're talking about, Elizabeth. Right? Let me go grab. Elizabeth asked that a while ago. And was there more questions on? I'm just going to focus on power here for a second. Crystal, did you have more questions about power? We do cover it a little bit earlier. Do you have any other questions about power? Power is controlled by 3 things: the sample size, how many samples you take, like the larger your sample. Type 1 is alpha. Type 2 is beta. That is correct. We got a little cheat sheet over here on that. Type 1 is, so I do 1, 2, A, B, plus, minus. It's not always that type 1 is a false positive, but I like to think of it that way. And the type 1 is when the null is true. The type 2 is when the null is false, and we fail to reject it. What is the first chapter of this test covered? Should be chapter 14. That's on the review sheet. Chapter numbers, and sometimes I'm like, wait, what chapter is what? What? Let me go right here and go grab that just to make sure. Yeah, it says topics. Yeah, here it is. I am always afraid of saying something like, since Brian said chapter 13, like, what? I'm always afraid, like I'll say a wrong topic chapter. Let's see what other questions there are. What is the first? Yep. And so Elizabeth had been asking about the chart. Elizabeth, please double check right here. I need to make this a button. I do not know why I have not made this a button. You know what? I should just make it a button then. 2 seconds. I'm going to make this a button right here while I do this. Elizabeth, is this the chart you are talking about? I'm going to make it a button while we talk about this. And I can use the button to turn it on off. Is this the chart you are talking about? Oh my gosh, I cannot. Oh, here we go. 2 seconds. Which one are we on? We're on the main screen capture. Main screen capture. Sorry, I'm making a button right here. Maybe I'll do this afterwards. 2 seconds, everybody. Brian's trying to figure things out. Desktop, that's where I'm at. It's driven me crazy that I haven't had it as a button. I use it so much, and I'll forget. All graphics were so close. Oh my gosh, I can do it now. Boom, we got it. Okay, it's a button now. Is that the graphic you're talking about? all graphics. Take Brian off the screen. Let's take a screenshot of it. This is really great for the tools and techniques. The tools and techniques, this is the graphic you want to know. So tools and techniques help right here. I think this is the one that people are wondering about. I'll worry about changing the graphic on that in a moment. But is this the graphic? Is this the droid you're looking for? So with this right here, you have right here the quantitative only questions right here. If you're just talking about quantitative, would be something like analyzing students' GPAs, analyzing how many pets people own. This is going to be your histograms, your bar charts. Can you go over degrees of freedom? Yeah. We'll end with a mosaic one. I think that's a good end right there because we haven't done too much mosaic. So we'll do some mosaic. You got it. You got there, Theodore. Someone else was asking mosaic a moment ago. So that is going to be like, we want to analyze students' GPAs. We want to analyze students' heights, students' weights, all quantitative questions. These graphics right here are going to be, we want to analyze something like, do you own a pet? We want to analyze, do you live on or off campus? Do we analyze, are you married? This is all going to be categorical data. These are both up here univariate displays of data, which means we're just displaying one variable. There's no X variable over here. It's empty. So what we want to then think about are these bivariate displays of data. And the first thing we started out with, or we really went in depth on, was QQ. So when we do this right here, what technique are we doing with scatter plots? Like if I want to analyze how far in miles someone lives from campus and maybe how much they spend on campus. So I have how far do you live from campus in terms of miles and how much do you spend on campus, like money-wise, what kind of technique would you use? Now, those are the graphics, but I'm trying to see if maybe the closer you live to campus, the more money you spend on campus. Like, is there some sort of word between it, like a linear relationship or some sort of, like positive or negative what? So how far do you live from campus and how much money you spend on campus? What techniques could we use? There's the graphics. We could do a scatter plot. We can't do a time plot because that's time on the x-axis. But how far do you live from campus and how much money do you spend on campus? What techniques could we do to talk about statistically if there's some sort of this to it or a linear relationship? Who knows? So we have here, how far do you live from campus, which is a quantitative variable. And so we're talking about QQ, straight enough, no outliers. What kind of tool could we use to see if there's some sort of linear relationship or what did these variables, positive or negative? We would want to look at either regression or correlation. So regression or correlation for these variables right here. We're doing a little tools and techniques right now. Down here, we have side-by-side box plots and histograms. This would be our questions that we've been asking tonight, like what is your GPA? Because that's quantitative. And do you own a dog? Like maybe dog owners have higher GPAs. So we can analyze the difference in the means. So this would be a 2-sample t-test down here. Great job, Leslie, right there. Yep. And so this one right here would be a 2-sample t-test because you're analyzing the difference between the means of the two groups. So you've got here your categorical X and your quantitative Y right there. Like, do you own a dog and what is your GPA? Next, we have over here, not to disappear, we have questions like, do you own a dog and do you live on or off campus? And in this instance, both variables are categorical. Like we're trying to understand, do you own a dog and do you live on or off campus? And this would be your mosaic plot, your contingency table. We don't really use stacked bar charts or side-by-side pie charts, but this is a pretty decent summary of the graphics. And once again, we would use chi-squared test of independence, which we're going to start talking about here in just a second. Logistic regression we don't cover in this class. That's why it's X'd out. I'm just going to X the whole thing out right there. But logistic regression is where you have a categorical Y that is covered in BAS 320. And I know some people are taking that, so exciting stuff. Let me reappear and let me head over here and get some data. We've already got data up. Let's do it. Okay. So this is one of the ones we covered yesterday. We're trying to see if there is a what between breaking a bone and the order you're born in your family. We're trying to see if these two variables are what of each other. The chi-squared test of independence always has what between the two variables. Hint, it's the chi-squared test of independence. So when we do the chi-squared test of independence and you see this graphic, if you ever see this graphic, you should put what between the two variables. Independent. Great job, Maria, right there. So you have independent. So we have the two variables are independent. So one variable, exactly. Great job, Caitlin, right there. I should have mentioned that. You are correct. If you're just analyzing GPA, that is correct. Caitlin, you are totally correct. That is 100% accurate. Great job. So these are where we say breaking a bone is independent of when you were born, like which order in your family you were born, because we have are you the youngest, the oldest, the middle child, and the people who are most likely to break a bone are the middle and the youngest, and the least likely to break a bone is an only child. We'll see more about this here in a second, but we're asking, is breaking a bone independent of the order you're born in your family, or the alternative, is it not independent? And that means the same as like, are they associated? Like, is there an association between these? So saying they're not independent is to say like, oh, you're the youngest? Well, of course you broke bones, but youngest, yeah, middle child too. The oldest and the only child, but are these differences by random chance? So let's go ahead down here and let's do a little bit of the calculations for this. What are the 2 additional conditions after random and 10%? Who knows the 2 additional conditions we'd need to check? So we're going to check one of them here. What are the 2 additional conditions after random, which means we randomly selected these individuals, and 10%, meaning we selected less than 10% of all individuals? So we have here that these need to be randomly selected individuals and less than 10%. And so we have to hope we have less than 10% of all people, which I'd assume we do, and we have to randomly select. So the third condition, and there is no technical order to these, but the third condition would be that all expected count data, great job, Kaylin, right there. All expected cell counts are making greater than 5, and then we have right here, and so expected cell count are all greater than 5, and then we have that it's count data. How do you check count data? Well, that's categorical, you're good. So count data right here means both are categorical. And then expected cell count means the expected cell counts are greater than 5. To find expected cell count, the formula is row total times column total over grand total. And the way you can solve this, and this is the expected, is to always just circle the numbers you want to do. I'm going to do the smallest one. It's kind of like if you go out with your friends and the youngest person is 22, then everyone's over 21. So we're seeing if the smallest expected cell count is greater than, so here's the smallest one, and we're asking, is this greater than 5? Brian just found the expected cell count for which one? When I solve this as a formula right here, and I'll write it, this is the expected cell count, like the formula I'm writing, which I've written twice now, is the expected cell count for which cell? This is how many blanks we would expect to blank a bone. So what is this expected cell count going to solve out for? And I'll solve it right here. But just look at what it crosses in on. So that's the answer right there. Is two-tailed t-test, quantitative categorical? It's quant categorical, correct, Kyle, right there. Because you'd be asking like, do you own a dog and what's your GPA? So only children who have broken a bone, I believe so. Because you just kind of go up here and, well, I would just want to grab one arrow. You would go up here and you would say, we're looking at the broken a bone. And then do you see where they cross? So they cross right there. Does that make sense how you just go to the row total for it and the column total. And so it won't be 25 yet. That's the count. So, it's also the observed amount. So this is the observed or the count. So that says count, but that's also known as the observed right here. So it's also called the observed. And sometimes in formula we call it the observed amount. Like how many did we count in this cell? Hence it's count data. So the expected count, and great job, Clarissa, right there, Crystal, right there, sorry. Excellent work. It is the practice that matters because we just keep working on it and we get it right. Got it. So 29.77. Let's throw everyone 100 points. Thank you so much, Crystal. And so 29.77. And that is the expected cell count. So that's how many we would expect to have broken a bone. Does that make sense? So if this is all just due to random chance, we'd expect 29.77 only children to have broken a bone. Now, Jump will do all this work for us, which is a great way to check to see if we did it properly. Fingers crossed. Yeah, we got it right there. And you can see we pretty decimal place accurate. Yeah, down to the decimals. So now we need to do a cell chi-squared. So to do a cell chi-squared right here, we need to take, and let's go ahead, and I'm going to re-graphic this. So just so we can see. So now let's do a cell chi-squared. The cell chi-squared, the classic famous formula, is observed minus expected squared over expected. So we're going to go here to the formula observed minus expected squared over expected. So good to see you here, John. Observed minus expected quantity squared. Be careful. Sometimes people have squared expected and it's quantity squared over expected. And this is the cell chi-squared. So this is a chi-squared for the cell. Like each individual cell has its own. What is the link to the speedruns? They're just on the main channel. I should put them in a playlist. Give me a second at the end of this. After this example right here, Maria, I'll put it all in a playlist and then I'll put it out there. And I don't know, hopefully they're all just like on the main video. Isn't there a way to find the degrees? Yep, we'll do that next, Theodore. That'll be our next thing. So I want people in this moment, I want you to try to figure out the cell chi-squared for this one. Now we would find all of them. Good to see you here, Hannah. So find the cell chi-squared for this. Go ahead and solve it. Just be working the mathematics. Find the cell chi-squared. So, and I'll put those in a, sorry, I forgot the playlist. No. It's going to be, I'm trying to solve it in my head as we're doing this. Maybe I shouldn't solve numbers in my head while I think I know it's going to be about 0.8 or so. Tell me if I'm wrong. Are the bonus emails and bonus points for the live class added on? They're added on at the end, at the very end. Great job right there, Amelia. You are correct. I was close in my head. I was thinking about 0.8. I had them on at the very end after all grades are calculated, and then you'll see final grade appear. Great job, Maria, too. So just make sure to be careful when typing this into your calculator. Is we want to do observed minus expected, quantity squared over expected, and there we go right there, 0.7663. Great job, everyone's got some great rounding right there. And so now we can double check our work once again. So it's always good practice. We go over here and we just ask jump to give us the cell chi-squareds, and what do we see? Boom, there's the answer. Does anyone know, can anyone add these numbers in their head for me? What is 0.45 plus 0.52 plus 0.1424 plus 0.163? Does anyone know how to add all those numbers in their head right here? Who knows? Can you add all these numbers in your head? I'm going to highlight the numbers I want you to add, and I want you to tell me if you can just add them all in your head. Wink, wink. So I want you to add all of these cell chi-squareds right here and tell me what you get. Everyone's going to be doing it in their head right now. No calculators allowed. So what do you get when you add up all those? Exactly. Wow, Leslie, that was just amazing right there. Just great job. This is the Pearson chi-squared test statistic, is the sum. If you take all of these right here and you sum them up, the sum of all these, sure, that says sum. The sum of all these right here is the Pearson chi-squared test statistic, and then the p-value. And so what does this p-value tell us? It tells us that we failed to reject the null. Because the p-value here is high, just let the null fly. Don't reject the null. The p-value is high, just let the null fly. Don't reject the null. But one thing I do want to point out, and I think it was Theodore asked, great question. How do we get the degrees of freedom here? You might have saw it, so don't cheat. We always say, Brian, this is a what by what, and I like the way this looks right now because I could see someone getting it wrong. I've had people get this wrong. Brian, this is a what by what. The degrees of freedom will be this times this. I've seen mistakes when people see this. It's a very common mistake to use the totals. Theodore, great job. Brian, that's a 2 by 4. And it doesn't matter which way you do it. 4 by 2, 2 by 4, either way. Because it's technically 4 by 2 rows, columns. But either way is fine. The degrees of freedom formula is going to be what times what. So we say, Brian, that's a 4 times 2. The degrees of freedom formula is going to be what? Brian, that's a 4 times 2. There's the degrees of freedom. So 3 times 1. Great job, Kaylin, right there. And Leslie and everybody. Good practice. And you just found the degrees of freedom right there. The degrees of freedom tell you the shape of the chi-squared distribution. So we can go to the chi-squared applet right here. Exactly. Lindsay putting some great stuff. Lindsay, wait. Lindsay, are you from previous semester? So I see names. I'm like, wait, Lindsay, are you this semester or previous? Because that's awesome right there. And if previous students came by and are just putting like formulas in the chat, that's even more. If you're current semester, that's awesome too. But if you're previous semester, that makes me smile even more to be like someone coming by and being like, hey, everyone, here's some notes. Here's something I remember from Stats 1. Like, that's awesome. Well, I love people putting the formulas in the chat right there. That's a huge help. Throwing out some points to everybody right there. But shout outs to all former and current Stats 1 students. It makes me smile when we see people like Julio swinging by. Julio's graduating. And we can see here how this is calculated. You are this semester. Okay. Totally fine. There's so many. The problem is like it's much easier when I see students in person because then it's so easy to remember, like, you remember a name and a face. And then there's wait, what you doing, p-value? Oh, that's the There we go. There's the p-value. No, it's so much easier. Lindsay, let's throw over another 100 points. Thank you, Lindsay, right there. It's so much easier when you see people and they come to your office hours. And like the last semester I saw students in person was like with Walker, and it's cool because Walker's from Texas. And so it'd always be like Walker, Texas Ranger and stuff like that. But it makes me miss having my office hours in person and seeing people, because you just have this, like, you get to know students a lot better when you get to see them in person. Like, I really think it's cool what we do here online, and I really appreciate everyone who's always talking. Do we multiply them together or just leave it? You always multiply. Bingo. You always multiply like we have right here. Great job right there, Leslie, and great question. Because then I always say it's 3 times 1, but then solve it mathematically. So the degrees of freedom are always going to be multiplied together. I'll do a big example, but like, I love what we do on YouTube, but there is something special about doing in-person office hours. You got it, Lindsay. Everyone give Lindsay some shout outs right there. That's some energy right there. We're all about that energy. So we are here to help out. Let's look at this right here. I'm trying to find one that doesn't have way too many levels like that. Let's look at... I don't know which one I'm going to pick. I swear there's another one. Oh, distance from campus. Who here can figure out the degrees of freedom on this one? This crazy one right here. Who here can figure out the degrees of freedom on this? See if you can solve it, and then I'll tell you how to solve it. I'm taking a moment to figure it out myself. Okay, I think I got it. See if you can figure out the degrees of freedom on this. Wouldn't love this as a test question, but it's totally fair. What are the degrees of freedom on this? What are the degrees of freedom? You have to say, Brian, that's a blank, but you don't have to say the first part. I figured it out. Can you? Is it double check? Double check, Theodore. That's what I'm getting. Brian, that's a 5x4. So it's a 5x4, and then reduce each hand down by 1. So 4 times 3. 4 times 3 are the degrees of freedom, because there's 1, 2, 3, 4, 5. So that's 5, reduces to 4. There's 1, 2, 3, 4. That's 4, reduces to 3. Degrees of freedom should be 12. Don't worry if you got it wrong. Here we're throwing, Theodore was first right there. We're throwing 100 extra points to Theodore right there, doing some practice. It's always hardest when you're the first person to answer, because you can't be like, oh, other people are answering that too. No. It's just the smallest. You miss one of the smallest columns, and you're like, missed the column. Yeah, that one right there. That's the tricky one. Oh, so you did 4x4. So 3 times 3, 9. Yep. Yeah, that is a little bit weird. That's because not a lot of people live. That's the width of that's amount of people who live 30+ minute drive. So you think there's very few people who live a 30+ minute drive. And you can see that over here. Where is it at? 30+ minute drive. Yeah, there's only 14 people. So that's why that is so small right there. Yeah, let's end with that. Kalen, that's a good answer. Good question right there. Which one do you want to do, Kalen? We will end with that. And I'm going to go eat, maybe sleep. I don't know. Let's head over here to space. Let's put on my chill music. And thank you, everybody. All the hard work. We're going to end with Kalen's question right here. I really appreciate it. I know it's been a busy semester. I know it's been crazy. And I really just want to say, like, having trouble with 6, I'm going to get question 6 loaded up here. I really mean it. Like, I couldn't imagine being in this pandemic and being a student. Like, I love walking around campus. I love, like, just seeing people. And the world right now is just, not as fun as it has been in the past. But be there for each other. Continue to help out each other. And that's probably what's most important. Stat 201 exam comes second place to helping out each other. And I mean that. I'm not just trying to be like all sappy. Be there for each other. Help out each other. Vols help vols comes before statistics. Vols help vols. Vol means all. Then study statistics. So I appreciate that right there. Thank you, John. No, I want people to know there's a positive environment where we treat each other with respect. We stay positive. There's not so fun things in life, like the COVID. But we stay positive and we work to help each other, because a positive attitude is going to beat out a lot of the issues we have. And I know it's tough, but we're going to stay strong, and we're going to solve question number 6. Let's do this. Let's make this happen. Here we are. Question number 6. Ooh. What does it look like we got right here? We got a histogram. We got maybe a t-test of sorts. We got to write a null and alternative. I like this right here. We got some nulls and alternatives. We got some t-tests. Let's make this happen. Patients arriving. Okay. I like this chill music. It's my favorite one, I think. Oh, Lindsay, thank you guys so much. I swear, like, I don't know. You guys make me laugh. Appreciate that. I don't know. I designed this class the way I'd want a class. That's when I work on this class, I'm like, I read what the students write too. But I'm just like, I want this class to be more than just like learning stats, which we try to do. Let's learn some stats. There's a lot of if you ever look at questions, when people write questions, they're always trying to set the scene of the question. So this question has a lot of stuff we don't need. We're going to try to figure out the things we need in this question right here. So let's find the things we need. What do we need in this question? As patients arrive at a local hospital emergency room, as long as they are able to respond and are not deemed to have an immediate life-threatening condition, they are asked some standard questions before being asked to take a seat in the waiting room. The time it takes to complete the initial set of questions, they call it triage? I don't know. Questions has come under scrutiny lately. The emergency room manager believes that the average amount of time it takes to answer the questions is 2 minutes. We have the average amount of time. What kind of variable are we dealing with? That's the first thing I really care about in this question. When I talk about what I care about in this question, when you hear average amount of time, what are you thinking data we're working with? Which there's a hint down below. What kind of data do you think that we're working with? Which this kind of gives it away down here. What kind of data do you think we're working with? Because you can see what that graphic is, and you can see some other stuff over here. We're dealing with quantitative, and we see that this is quantitative. We have histograms, so it's very important to notice first thing that we're dealing with a quantitative variable. So we're going to mark that and be like, okay, I'm dealing with a quantitative variable, and that means we're dealing with the mean. So we'll go ahead and identify this. This is the toughest one to identify for this problem. What is that? What is that? They believe this is true. This is their current initial starting out belief. This is what they believe is true in this moment. So what is that? It's their starting belief. That is their starting out belief. And this is the notation I think people usually forget. And if you know what that is, it makes the problem a lot easier when we get to this question right here. You're basically right, Kaylin, and I think you know what it is. Like I think you would use it in the right spot because this is mu naught. That is mu naught right there. So it is relative to the null hypothesis. So when we look at where we're going to use it down here, we would go right here that the null hypothesis states, and so since we're testing the mean, because we have quantitative data that we're testing, we're going to go right here and write mu, and we're going to say that it's equal to mu naught. Now I'm going to replace mu naught, kind of like Lindsay, right? It's pretty much what we expect to see. So yep, that's it right there. It's mu naught. So it's the hypothesized current initial belief. So it is 2 right there. And so that is what they currently believe is true. So we're saying, yeah, they believe the null that the true mean time it takes for someone to be triaged in is equal to 2. Great job, Crystal, right there. And here we see something else. A nursing school intern was asked to randomly select incoming patients over a 2-week period and time how long it takes to get answers. The following are some of the results. Right at the null hypothesis indicated by this problem. Okay, here it is. I thought there was something. Most emergency room people believe it takes longer than that. So this is another important part. This is going to tell us the what of the alternative, because they're saying there's people who believe otherwise. Like there's people who are saying, no, that belief you have is not true. There's evidence of this. Like you should believe this. Some sort of something to what they believe. Exactly. Great job right there. This is the alternative that we're looking to see if it's evidence for us to believe this is true. So we have here that the true mean time it takes, so I'll just read it. The alternative states that the true mean time it takes for patients to be triaged in the emergency room is greater than 2 minutes. Is there evidence of this? So we go down here, we've got the output. Consider it. Let's go ahead and mark this output just a little bit right here so we know what we're seeing. We have here y bar, that's the sample mean. We have here s, that's the standard deviation. This is actually s over square root of n. I'm speaking specifically about the standard error of the mean. And you've got here your confidence interval portion for the upper and the lower of the confidence interval. So if you were to build a confidence interval down here, your upper and lower of the confidence interval would be there. And at the very center of the confidence interval, I hate it when it does that. At the very center of the confidence interval is the mean. So we could highlight that right here, but your upper and lower are right there, and you could figure out the margin of error. So lots of things we can do with this, but if you just look at my color coding right here, I'll write in the numbers just briefly so you can see. This is where 2.24 is at because that's the sample mean. This is where 2.36 is at. I'm going to round this. Who can tell me the margin of error for this interval? I think it helps when you visualize it to see what's going on right here, but who can quickly come up with the margin of error? I'm just going off of what the output gives me right now to kind of take some notes as I look at maybe what this question asks next. Who can tell me what the margin of error of this interval is, which we can get from there also. And then I can tell you, I can already see what we're doing because I'll put something over here on the right while you're thinking about that margin of error. The margin of error is, great job. I think people are doing it a little more exact than I have decimal place right here. Yep, so if you wanted to, you could calculate it more exactly by carrying more decimals, but the margin of error is this right here, at least the way I have it written. Great work right there, everybody. Another 100 points. This is the practice we need, and maybe you can tell where this question is going, at least with the information we're given, because I also marked something else. I marked the null value we are testing, and I'm showing you that the null hypothesis is actually outside the interval. So let's think about, let's see where the question's going. Okay, so the next part says, use the information in the output to calculate the value of the test statistic for the hypothesis test. So here we'll take a good screenshot of all this. Okay, so they give us all this information right here. And I think it's going to go off the page. Well, so be it. So when we do the hypothesis test right here to get the T, where's the link for the speed runs? I'll be posting it here at the very end. Great reminder. Thank you for reminding me. They are the links. If you go to the videos, the most recent ones, they will be there. And so now we need to go and plug in the numbers. Null is not included, not sufficient enough data to reject. Oh, no. So we are going to reject it, Lindsay. Yep. When we get this right here, we will reject. And then briefly explain your reasoning. You probably say that the p-value is not included. The t is going to be pretty large right here, 2.24. I'm going to do a rounded version. So we hypothesize 2. Remember, we wrote this down as the hypothesize. And then the standard error, which we could solve by doing s over square root of n. Sample size right here is n. I forgot to mark that. And we could do that, but it's 0.06. So the standard error, that's the standard error, is 0.06. And it looks like this is going to be a t of about 4. Great job, Ben, right there. Great job. So this is going to be a t of about 4, which is very large. I'm just doing a rounded version right here. You should definitely carry all your decimals. Please carry all your decimals. But I like to just, at least it's easier to write and see that we would do right here, if you're wondering about the calculations. And I'll maybe go and find the exact number so people can see. And then you divide that by 0.06, and there's the t statistic. The exact calculation is going to be the sample mean. Like if I was taking a test, I would go all decimals right here. And now we subtract 2, and then we divide it by the standard error, which is this. And we're going to get something very close to that, probably a little bit bigger, like 4.08 or something. How close was I? I say 4.08, 4.03. Very, very close. Very, very close. So either way, it's about 4, and that's a very large t statistic. And also, if you notice in this example right here, we give you a very large t. I think you could use 2 lines of reasoning to reject or fail to reject the null. Is you could say we reject the null because the t statistic is very large. It's much greater than 3. And when you look at that, that's going to be multiple standard errors away. So a small visualization of it would show something like this. What's up, Knox? Good to see you. Yes, you are. You're last semester, right? Like, just seeing people swing by. I'm not wrong on that one, but no, it's so good to see you, Knox, in here. I am 99% sure on that one. I'm 99% confident last semester, and so good to see you here in the chat, just here reviewing. Tell me if I'm wrong. Tell me if I'm wrong. I might be wrong. Let's go ahead and go to the t-applet. So we're going to go right here, put in the t-value we found, not that t-value. Let's go here and go t-value and degrees of freedom 31, and they were looking for greater than, and yeah, that p-value is non-existent. The p-value is basically 0. You would not have to do this, but if you look at the drawing right here that we made, it's non-existent, but you could also use the confidence interval to reject the null. So this semester, my gosh, okay, my brain is just not, my brain only knows stats, Knox. It only knows statistics. That's all my brain knows. I don't remember anything else beyond how to do t-tests. I think that might be the end of this question. I need to go, is there one more? State the remainder of your conclusion for the hypothesis test. Be sure to state it in context of the problem. We reject the null hypothesis that let's go look at that. We reject the null hypothesis that the true mean wait time is equal to 2 minutes. We have evidence that the true mean wait time is greater than 2 minutes. So we reject the null hypothesis that the true mean wait time is equal to 2 minutes. We have evidence for the alternative that the true mean wait time is greater than 2 minutes. And I think that should do it. I can't imagine unless it asks about confidence interval. There we go. I do love these questions. What was the T? Yeah, just divide these numbers. Do we use the alpha level at all for part 3? I don't think it says to use an alpha level, right? There's no alpha. Oh, wait, use alpha 0.05. So this one is a bit tricky because if you use the drawing, oh, I know why. Because they're talking about the confidence interval right here. Yeah, so that's the best, probably one of the best answers right there. And so really great comment right there, because if you look at the interval right here, you could say, you know, the right here, this would be good enough to reject at the 0.05 level on the two-tailed test. And the two-tailed test is just going to, so actually I have an issue with my drawing. The two-tailed test is going to have twice the p-value. So if we can reject on the two-tailed test, we can reject on the one-tailed test. So we are interested in this test right here. And we can actually reject on this test for the two-tailed test. Which reasoning was it? Luckily, there's not really many written tests right here, but probably I would say the best reasoning, because it's evident by the interval, is that since the interval does not contain the hypothesized value, it can be rejected at the 0.05 level on the two-tailed test with 0.05 alpha. So we have a 95% confidence interval, and then we can reject at the 0.05 level of significance for the alpha level. Does that make sense, Lindsay? I think it's got it. Woo! Did some 2-hour review. It's 10:30 in Knoxville. Let's go ahead. Let's go to space right here. We'll put on a little more music. Thank you, everybody. Good practice. Let's put on, there we go, second favorite song. And then we'll hop here to space. I'm going to go ahead and make this playlist so I don't forget. Don't want to forget. Don't forget. And 37 people watching right now. That's awesome. Thank you, everyone who's tuned in this moment. Turn up the music just a tiny bit. Go to playlists. Go to new playlist. Title, test 3, speedruns. And there we go. Oh my gosh. There we go. Create. And give me a second. Test 3 speedruns. I will put this in the chat right here. What? Didn't I just create that playlist? Oh my gosh. Let's create another playlist that add title. Test 3 speed runs. Create. Test 3 speed runs. Got it. Here we go. Add videos. Add videos. Your videos. And let's put this in there. We'll put it at the end right here. Final review contest speedrun. I think he puts them in order. So let's go here. 14, 15, 16, 17, 19, and speedrun business analytics. There we go. Add videos. And there it is. And I put them in order. And there it is. Let's go back here. I might do a little bit of live review. You're welcome, Leslie. You're welcome. Thank you, Leslie. Thank you, Lindsay. Awesome. Yeah, join in anytime. Just join in, say hey, like, especially if they send you links or anything, be like, hey, I'm just joining in, just swinging by, and I'll probably be like, wait, you're this semester, right? And you'll be like, no, Brian, I'm last semester. Come on, Brian. Thank you, Crystal, and everyone. Great review, Crystal. Great job. Great, excellent work right here. Good to see you here, Sam. If you have questions, let me know. Last questions, just put the link for the, let me see if it loads. Open a new tab. It does work. It works for me at least. No views. No. Stream crash. Wow, I'm glad we just crashed in that moment. Random stream crash at the end. Hey, you know what? We went the whole stream without any issues. No one was saying like, you know, it's not working. We might be streaming on a whole new video right now. I don't know if you crashed for too long. I looked over and the thing was red. I wonder how long we were crashed for. But the link, did people get it? They might not have gotten it. So let me redrop the link right here. No views. No one's found it. Well, we'll find out. If you're still here, feel free to say bye. Because it's time, everyone. It's time to go. Get some sleep. Relax. Bye for now, everyone. Bye. Don't crash any more streams.